to incorporate risk into the decision-making process in our industry. Our job is to provide that vital ingredient, an assessment of the probability that something will go wrong. Now, that may sound obvious, but I don't think it is very obvious when important decisions are made on how to build models. So models, as I just said, are often built under the premise that we can simulate what happens under the ground. Well, that's not why we should be building a model. We should be building a model so we can quantify and reduce the uncertainties of decision-critical predictions. Now, simulation helps here, but the primary purpose of simulation is to serve a greater goal. And that greater goal is risk assessment. And unless that greater goal is part of how we build that model from the very beginning of the modelling process, we're not going to do it properly. And we mostly don't. So we're told, it's in all the textbooks, when you build a model, you start off with a conceptual model. And that's the geologist's idea of what happens under the ground, where water enters a system, where water leaves a system, and what affects the flow of water. Well, that's okay. We can't dispense with the conceptual geological model, but I'd suggest that just as important in the conceptual model on which the numerical model rests must be the flow of information. And if that isn't in the front of our minds when we build a decision support model, we're not going to build it properly. Because what is information? Information, by definition, is whatever it is that can reduce uncertainty. Information reduces uncertainty. And our job is to quantify and reduce uncertainty by assimilating all available information. So our model must be built, yes, to simulate movement of water, but for a reason. Not because we simulate it very well, because our task is to facilitate flow of information. Information from wherever it resides to the predictions on which decisions rest. And unless a model is designed from the ground up to facilitate that flow of information, it won't do it very well. And that's why, in my opinions, a lot of models aren't doing very well. So if we're going to talk about flow of information, if we're going to talk about uncertainty, we have to talk about Bayes' equation. Now, I'm not going to show any equations on which groundwater models are based. I'm not going to show any of the partial differential equations that we think and we hope that groundwater obeys as it winds its way through the subsurface. The only equation I'm going to show is Bayes' equation, because this is the equation which all simulation must serve if simulation is to serve decision support. And I'm sure you've all seen Bayes' equation before. And Bayes' equation says that everything we do really should be discussed in terms of probability distributions. Probability, because nothing is certain. Nothing is certain. So the whole data assimilation process, the whole modelling process is all about handling probabilities. Probability distributions associated with the properties of what's under the ground, probability distributions associated with decision-critical predictions. Bayes' equation says we start off with uncertainty. That when we go to a site and characterise that site through drilling, geological mapping, point measurements of hydraulic properties, we learn something, we gather information. But we still don't know too much about the properties under the ground. We know something, but interpolating between what we know to a three-dimensional heterogeneous subsurface is full of uncertainty. What we know about under the ground can only be characterised probabilistically, the so-called prior probability distribution in Bayes' equation. But then there's another source of information, a different but important source. It's the behaviour of the system. It's the heads we measure in wells, the contaminants we measure in the ground, the flows into streams, the behaviour of the system. The beauty about simulation is it can incorporate both of these types of information. Hydraulic properties that we know or that we know probabilistically can be reflected in a model's parameters. Those parameters can be adjusted until the model is able to replicate what we can measure of system behaviour. And in so doing, we're assimilating the information content of those measurements. And once we've done that, once we've mixed those two very different types of information from two very different sources, the prior probability that emerges from expert knowledge is hopefully narrower because of the information content of system state measurements. And then through modelling, we achieve the so-called posterior probability distribution of parameters and then decision critical predictions. So this is what modelling is doing for us. Well, this is what it should be doing for us. If it's not doing this for us, it's not serving the decision-making process. Simulation and all the beauty of simulation and all the mathematical wizardry of simulation, all the partial differential equations that underpin simulation, in the end, they have to serve Bayes' equation and not the other way around. We don't build a great big complex model and then calibrate it and think that we're doing the right thing. Simulation, it should serve Bayes' equation and not the other way around. Simulation should be built to serve Bayes' equation, and then simulation is serving decision support. And then we are doing decision support modelling properly. Okay, so where does the calibrated model fit into this? Well, if you look at Bayes' equation actually doesn't say anything about calibration. The calibration implies uniqueness, and Bayes' equation said everything is characterised probabilistically. Where is this unique parameter field with which the calibrated model is endowed? Well, it's not there. Uniqueness, the calibrated model, is an artificiality. It's not part of Bayes' equation. However, it is convenient sometimes to seek uniqueness. Numerically, it's convenient. It's also a convenient way of testing the hypothesis that our model is a worthy simulator of processes underground. It's never very good, but worthy enough to be used in Bayes' equation to quantify and reduce the uncertainties of decision-critical predictions. And if we do calibrate a model and seek uniqueness, the justification is testing the adequacy of the model. And if we do everything correctly, the predictions made by the calibrated model hopefully will lie somewhere near the centre of the posterior probability distribution of those predictions. But we don't stop there. We still have to quantify uncertainty if we're going to help people make decisions. And until we do, we're not doing the decision support thing properly. So, the other thing before we get on to another topic is the fact that when we do decision support modelling, we have to live in a highly parameterised world. Now, in the old days, we were often told, don't use any more parameters than you need to calibrate the model. Parameter parsimony is the rule. These days, it's different. We need to live in a highly parameterized world. Now, I'm not saying that the structure of the model need necessarily be complicated, but more often than not, even a fairly simple structure, and I'll show you an example shortly, should be endowed with a lot of parameters. Why? Firstly, having lots of parameters doesn't cost us very much at all with modern technology. Secondly, We need to assimilate data. We need to fit data well, provided the model's good enough to do that, provided there's not much noise associated with that data. If we have a lot of parameters, we do get the minimum error variance solution to an inverse problem. It gives the inversion process freedom to introduce heterogeneity where it needs to be introduced. More importantly, it prevents us putting its false heterogeneity where there's no information about heterogeneity because we don't have enough parameters to differentiate between where heterogeneity is needed and where it's not. But even more importantly, if we just take what I've been saying seriously, it's the parameters that you can't estimate that are just as important as those that you can, because it's the ones that you can't estimate will often be responsible for the most uncertainty associated with decision-critical predictions. They need to be there, not because they can be estimated, but because they can't be estimated. So we need to live in a highly parameterized world, and we need to have the technology which allows us to do so if we're going to do this decision support thing properly. So this has big repercussions. And the first repercussion is that the idea which most modelling serves, that you pay someone to do a model and then they deliver the calibrated model, that just doesn't make sense to me. Modelling is a process. It's not a deliverable. It's a process of assimilating data. It's a process of testing hypotheses whether bad things will happen or not. And a simulator on its own cannot implement Bayes' equation. A simulator on its own can simulate. Other software is needed for history matching, data assimilation, that is calibration, uncertainty quantification, and some of the other tasks that accompany simulation. Simulation on its own does not support decision-making. Simulation is one tool among other tools that are essential ingredients of decision support modelling. And these other tools, well, they're like PEST, PEST++. As Alberto said, I wrote PEST. PEST++ is written by the next generation, Jeremy White and people who are working with him, and Dave Welter, the original author of PEST++. But between PEST and PEST++ or other software which does similar things that other people may write, it's these dancing partners that are just as important as the simulators if we're going to do decision support modelling correctly. And these dancing partners have two fundamental design specifications. The first thing is they've got to have a non-intrusive interface with the model. Now, what do I mean by non-intrusive? It means I don't want to have the model's source code, and I want the model to be as complicated as it needs to be. There might be 1 or 2 or 3 simulators involved here. There will undoubtedly be parameter pre-processors and model output post-processors. These will be in a batch or script file, and I need to build whatever model is best for a particular case and interact with that model through the model's own input and output files. So that's the first fundamental design specification of a model dancing partner, that it have a non-intrusive interface with the model. The second fundamental design specification is that dancing partner can parallelize model runs. Now, these days, computing hardware allows us, it's all about parallelization on a single computer or on multiple computers in an office network, on a high-performance computing cluster, on the cloud. We can get so much computing power so cheaply on the cloud. Members of the PEST and PEST++ suites have an architecture like this. There's a run manager, and this does the magic, this does the inversion, this does the data assimilation, this does Bayes' equation. But as model runs are needed, and hundreds, thousands of model runs are needed, these model runs are commissioned. They're done by agents that can reside on the same computer or on different computers with communication between them done using TCP/IP, that is the language of the internet. So between those, non-intrusive interface, parallelization of model runs, we can dance, we can do decision support modeling so much better today than we could just a few years ago, but according to rules which enable this to happen in the best way possible. But as I said earlier on in this talk, this isn't going to happen if we build a complex model and then do the dancing as an afterthought. The model has to be able to dance. Hopefully, it's got to be able to run fairly fast. It's got to be numerically stable. And that means it's probably got to be built to make specific predictions. The idea that we build one giant, horrible, complex thing that can make any kind of prediction, that doesn't work. The model has to be built in a way that is optimized to make certain types of prediction, is stable, runs fast, can dance, work with PEST to assimilate data pertinent to that prediction. Then it can quantify and reduce the uncertainty of that prediction. Then it can serve the imperatives of decision support. So before I go and show some examples, I'll just show you a few resources. I've covered this whole topic very quickly. There's so much more to talk about. It would get a bit boring. My job is not just to educate, but to entertain. So I'll start entertaining shortly, but with some examples. But first, I'll just point you in the direction of some resources. So PEST++ can be downloaded from the PEST++ GitHub site. Documentation and training material, software which facilitates setup of PEST++, all written in Python from the PyEmu site. There's the PEST site from which you can download PEST. All of this is free. Documentation, training videos, roadmaps, the PEST book. Training in decision support modeling and other aspects of hydrogeology is available through the HydroSimple, and links to all of these things and other information is available through the GMDSI website. GMDSI is a project that I'm involved in. GMDSI stands for Groundwater Modelling Decision Support Initiative, and its job of this project is to kind of say what I'm saying now, but also demonstrate by worked examples that this is the way that modelling should go, and then give people help in moving modelling in that direction. Okay, so let's move on to some examples. Firstly, I'll just talk about calibration. So this is where we're achieving the minimum error variance solution to an inverse problem. So this is actually a decision. You can download the report on this model from the GMDSI website. And I think this is an excellent example of contrasting the old way and the new way of doing things. Originally, a very expensive model was built that tried to simulate very complex geology. This is in a mining area in Western Australia where iron ore is mined. And the geology is steeply dipping metamorphosed rocks, and the ore body lies in this rock here. So the original model took a long time to run. And the idea was with 7 layers and zonal parameterization to try to simulate what geologists thought they knew about the geology. The trouble is that in complex areas such as this, the geology is always full of surprises, and that as well as the steeply dipping stratigraphy, there's faults everywhere. Water will flow through faults, and faults can offset the stratigraphy. Because the model took a long time to run and because it was cumbersome, it didn't do a very good job of history matching. And there was some important information there to be gleaned from history matching, particularly from a series of pumping tests that were done. They had to, at the stage when the original model was built, the mine hadn't been started. It has been started now, but an important decision was building a pipeline that would convey the water that was required to dewater the pit. They needed to know roughly how much water would be required for this, and it was seriously underestimated through previous generations of modelling. We revisited this job recently and decided to try to demonstrate the concepts that I've been talking about using a very different modelling approach. The approach was at the opposite end of the spectrum. Basically, fit the data first, ask questions later. The idea being that there are 6 pumping tests that were done here, and drawdowns were monitored in a variety of wells. And was there information here that could have foretold the fact that inflow to that pit was going to be larger than the original model had predicted? So there is, again, structurally very complicated, but we wanted a model that was fast-running, structurally simple, but parametrically complex. So it was endowed with about 3,000 parameters, but it was sleek and fast. Fairly easily, we were able to replicate the drawdown in all of those wells in response to the 6 pumping tests by fitting them simultaneously. And patterns like this emerged through the history matching process. Now, some of the patterns followed the stratigraphy. Some aspects of the patterns followed what was known about the geological structure. Some aspects of the patterns were a surprise. Now, I'm not saying for one moment that this is a picture of under the ground, but I'm saying it has told us stuff that we wouldn't have found out if we hadn't built a model whose job was to assimilate data. We did fit first, and then we asked questions later, and we were able to answer some pretty important questions, even with an abstract representation of what was prevailed under the ground. It hasn't got to be realistic. We're never going to be realistic, but we can often find out what we need to know, even with abstract representations. But if we don't assimilate that data, we will never know. So we fit the data well. We are able to quantify the uncertainties associated with parameters and predictions of pit inflow, fitting not just hydraulic conductivity, but specific yield. And we were able to draw some pretty important conclusions that geological structures have a big effect on flow here. Not only that, but these structures connect the pit area to sources of water. In other, a limestone aquifer here, and possibly overhead in alluvial aquifers. This in turn will actually require that you pump more water than you thought you had to pump, with uncertainty taken into account. So we did our job. Do we have to know exactly what's happening under the ground? No. Do we have to give estimates of uncertainty that we can guarantee will include the right answer? Yes. And we had the benefit of hindsight here. We had the benefit of knowing how much water that pit has to extract, and the correct answer was within the uncertainty limits. But we built a model to assimilate the data that had the most chance of telling us what we needed to know, and departed from convention in doing so. The model wasn't built to look like a figment of a geologist's vivid imagination. It was built to assimilate data, and it did the job. Now, just in the interests of, this is another model built by colleagues of mine. It was more complicated, and it too, highly parameterized inversion, was able to assimilate data, assign hydraulic properties to a much more complex domain, and we were able to predict and quantify my colleague, the uncertainties of pit inflows. So now let me move on to uncertainty analysis. Uncertainty analysis. So the way that works is that we have our model and that we run it under historical conditions, and we calculate a sensitivity matrix. We run it into the future. We calculate a sensitivity matrix. So this is sensitivity analysis in a way, but much more informative than traditional sensitivity analysis. A lot of people, they want to do sensitivity analysis, but often they want to do it for the wrong reasons. In the old days, we had to do sensitivity analysis. We were told in order to tell us which parameters we could remove from the inversion process because we couldn't estimate them. Well, these days, it doesn't matter. These days, as I'll show you shortly with even the latest technology, the number of parameters does not matter. We don't have to remove parameters. In fact, we mustn't remove parameters. Their non-estimability is imperative. It's an important part of quantifying uncertainty. Linear analysis can often give us profound insights into that whole flow of information that decision support modelling is meant to serve. And as such, it's often, but not always, worth doing. So we've got the past, we've got a sensitivity matrix. In the future, we build a sensitivity matrix, often called a Jacobian matrix. So this is local sensitivity analysis, but local sensitivity analysis on steroids. Based about these calibration and predictive Jacobian matrix. A Jacobian matrix, these are just partial derivatives. That's how we populate a Jacobian matrix. So, without going into the details, with utilities available through the PEST suite and through the PyEmu suite, once we've calibrated a model, we can come up with graphs like this. This is a fairly simple model with only 57 parameters. It's an even simpler one. This was a surface water model, actually. But we can give each parameter a rating called the identifiability of that parameter. If the identifiability of a parameter is 1, then it can be estimated uniquely on the basis of the calibration data set. If its estimability is 0, the calibration data set says nothing about it. If it's got an identifiability between 0 and 1, then the calibration data set says something about that parameter, but not enough to give it a unique value. That information that is there in the data as it pertains to that parameter is shared with other parameters in ways that cannot be broken. So we can graph identifiability, we can map identifiability. We can show that where there's more data, the identifiability of the parameters is greater. And this can be instructive. Again, what's decision support modelling all about? Flow of information. Identifiability gives us some insights into the flow of information. Or we can go even further than that. So this beautiful matrix equation that's now on your screen is actually Bayes' equation in a linear world. There's our Jacobian matrix. These other matrices are covariance matrices. So if we're doing sensitivity analysis, we're living in a linear world. And this is the utilities available through the PEST suite. Take those linear things like Jacobian matrices and compute the uncertainty of decision-critical predictions using Bayes' equation under the assumption that linearity prevails. It's only an assumption, but the insights are huge. So straight away, here's the posterior uncertainty of a prediction, easily calculated using a matrix equation. There's the prior uncertainty of a prediction. This is how much that uncertainty has been reduced through history matching. That's useful information. We can take that equation and draw maps and apply it to parameters. So here I'm calculating how much has the uncertainty of all parameters within this model domain been reduced through history matching. Again, higher, much higher reductions where there's more data. But maps like this one in particular, demonstrated to stakeholders that here is a very expensive calibrated model. But in some parts of the model domain, the uncertainty associated with parameters and by implication predictions made in this part of the model domain are going to be no less uncertain than if the model hadn't been calibrated at all, because the calibration data set isn't informing these parameters. And this allows people to see where uncertainties have been reduced and where they haven't been reduced. The graph I showed you before of inflow to the pit, it was calculated just using linear analysis. So we can quantify the uncertainties of decision-critical predictions using linear analysis. Graphs like this can be very useful. We can ask, what is the contribution made to the uncertainties of decision-critical predictions by different parameters or groups of parameters? Now, this just isn't academic. This is important stuff. If I've got to build my model to be sleek, efficient, and fast running, I've got to make compromises. I've got to try to obtain parameterization complexity, but I may have to make it structurally simple in certain places. Have I biased my predictions through being too simple? We can test that using linear analysis. Suppose I replace a large part of the model domain with a boundary condition. I can use linear analysis to ask, what is the contribution made to the uncertainty of a decision-critical prediction by that boundary condition? Back row before calibration, front row after calibration. If that boundary condition contributes little to the uncertainty of my decision-critical prediction compared with other sources of uncertainty, and if by simplifying that model I can actually reduce those contributions through data assimilation, then I'm ahead, and getting ahead through appropriate structural simplification hasn't cost me anything, because I've demonstrated that contributions made to the uncertainty of that prediction through simplification are okay. So linear analysis can give us it can show us, show other stakeholders that what I've done in building this model specifically to meet the imperatives of decision support, it's all okay. And then coming back to this equation, yes, it's approximate, but because it's linear, I'm assuming a linear world, and Bayes' equation becomes this matrix equation, nowhere in this equation is either the value of a parameter or an observation, yet I can quantify the uncertainty of a decision-critical prediction. Now, this has got big ramifications. I can now ask, what is the worth of new data or data that I've already got? What is the worth of data? Data has worth in proportion to its ability to reduce the uncertainties of decision-critical predictions. I do not need to have gathered that data to assess its worth, because the value of the data that I'm thinking about gathering does not feature in this equation. Yes, it's approximate, but linear analysis gives me the means to discriminate between data that has high worth and data that has low worth. I repeat, it's approximate, but the insights can be profound. So I can look at data I've already got, look at data I'm thinking of gathering, and compare their efficacy in reducing the uncertainties of decisions that I care about, and maybe use this as a partial basis for acquisition of further data. So linear analysis the didactic worth is huge. Now let's move on to nonlinear uncertainty analysis. And here, the new kids on the blocks are ensembles. And PEST PPIES, a member of the PEST++ suite, brings to us the iterative ensemble smoother. Now, the beauty of ensembles is that the cost of history matching is independent of the number of parameters. Whether I've got 1,000 parameters, whether I've got 100,000 parameters, the cost is the same and may only be a few thousand model runs. Yes, there are a few little, it might cost us a little bit in terms of introducing small biases. In some cases, ensembles are not the greatest if you've got lots and lots of data. They operate best if there's a large null space. But there are many, many, many occasions in decision support modelling where, with a comparatively small numerical cost, the ensemble smoother can serve the decision support imperative exceptionally well. Now, the way they work is like this. So we've got a model, we've got a set of parameters and set of outputs, and here's our field data. So we've got a prior probability distribution born of expert knowledge, site characterization. We sample that, generate a whole lot of realizations from the prior probability distribution. And yes, there's assumptions here. We assume it's Gaussian, but often that's not too bad an assumption. Not always, but mostly it's all right. We run the model and we get corresponding model outputs. Then from the covariance between the outputs and the parameters, we build an approximate Jacobian matrix. It's approximate, it's ranked efficient, but as long as we've got enough on realizations in this ensemble, enough realizations to span the solution space, if you want to be mathematical, this is enough to be able to take the differences between model outputs and members of the calibration data set. There is enough information here to calculate an improvement to these ensembles so we get a better match with the data, and then improve them again, and then improve them again at a cost of a few hundred model runs each go, until those samples of the prior have morphed into samples of the posterior. So we can then quantify the uncertainties of decision-critical predictions. So here's an example, and this is another GMDSI report, which you can download from the GMDSI website if you're interested. Last year, I and some colleagues were asked to look at water supply security for a small town about 300 kilometres north of where I live. That small town named Biggenden draws its water from a couple of wells in an alluvial system. How secure is this water in times of drought was the question. So we built a model. There's not much information here, but there is enough to tell us something, as I'll show you in a moment. Water levels were monitored over about 15 to 20 years in observation wells within the alluvial system. So he built a model using ModFlow 6, bunched up a quad tree refinement around the creeks. We had a recharge model as well, so the recharge, different versions of this lump-rem recharge model. You can download that from the PEST web pages if you want. Fed different parts of the model domain. Lots of parameters, because as I said before, parameters don't scare us anymore. We're not scared of lots of parameters. The model ran quickly. We were able to calibrate it using a standard methods based on Jacobian matrix, and then we used PEST PPIES to do the uncertainty analysis. So parameters in the middle of the model domain. And the new philosophy is if you don't know it, you don't have to assume it. It's just a parameter. It can wiggle. So you don't have to base your model on a litany of assumptions anymore. You just use modern technology to apply Bayes' equation based on the fact you don't know anything much. You know a bit, but you don't know a lot. It's there and part of the decision support modelling process. So we were able to get really good fits with the data that was available. You get used to fits like this when you're using PEST. And then after calibration, we use the ensemble smoother to get 500 parameter fields. that also gave us good fits with the data. And at the end of the day, here's a sample of those 500 parameter fields. They're all different. They all fit the heads in these observation wells really well. They all give us a representation of heterogeneity within the alluvial system. That's hydraulic conductivity, specific yield. And then when we make a prediction, we make it with all of them. So in this case, the prediction we're interested in is water supply security. If we take a realisation of future climate, are there going to be times when we don't get the water we want? So we build up this exceedance probability curve. The dark line was done just using the calibrated model. But there's uncertainty in our estimates of security. Using the brown and pink lines, we make that same prediction using the 500 calibrated models. So decision makers can then take into account the fact that we have some knowledge of what's under the ground, but there's a lot we don't know. There's uncertainty in our ability to predict security, and then depending on their risks, their ability to, their desire to take risk or not, they can decide whether to supplement the water supply of that town according to the assessment of risk, taking into account our lack of full knowledge of that alluvial system. So I've got one more example and then I'll be finished. All the methods that I've shown you are good up to a point. However, they're all one way or another based on a Gaussian probability distribution. And sometimes that doesn't serve us very well. The thing that can defeat us when we're doing uncertainty analysis is connected permeability, when water or contaminants can move through geological or structural features that cannot be described by something as simplistic as a Gaussian probability distribution. How do we operate them? Now, this is a field of current research, not just in groundwater, but certainly in the petroleum industry, and that's where ensembles came from, the petroleum industry. And there are a number of ways, a number of tools that you can use to address these particularly difficult problems of estimating uncertainty, where uncertainty is the outcome of flow of water or contaminants through features which can be continuous or can be impeded by features which are continuous, which may or may not exist, whose continuity is unknown. These, in some certain circumstances, can have the overriding effect on the uncertainties of decision-critical predictions. So there's a number of ways we can do this. I'm just going to demonstrate one, which is direct hypothesis testing. And I'm going to demonstrate it by showing you an example of a model I did quite a few years ago, which illustrates how this is done. The idea is that we've just calibrated a model. We've just history matched. We've just got the minimum error variance solution to our inverse problem. We've demonstrated that simulator may not be perfect, but it's good enough to be able to fit the data. It's good enough to be able to fit that data, giving us parameter fields that we can relate to the geology and what we know of the hydraulic properties in the area. So we've history matched. But we recognise the link between the parameters and the hydraulic, the hydrogeology, and we can fit the data. All right, hypothesis. There's a bad thing we don't want to happen. As I started off saying, that's what management is all about, avoiding the eventuality of bad things. Now let's pretend, as groundwater modelers, let's pretend just for a moment that we're actually scientists. And what do scientists do? Let's pretend we're science instead of witch doctors with crystal balls that predict the future. let's entertain the possibility just for a fleeting second that we're scientists, and as scientists, we're going to test hypotheses. That's what scientists do. Let's test let's say, can we reject the hypothesis that this bad thing will happen? How can we do that with a model? How can we make a model into a scientific instrument? Well, I've just calibrated my model, like a scientific instrument. Now let me recalibrate this model. Now let me match the past, and at the same time, I'm going to match the unwanted future. Now, if I can continue to match the past to the same level I matched it before, and if I can also match the future, and if the parameter field that emerges from this simultaneous inversion against past and future, if that parameter field isn't unrealistic, if it can be judged to be still okay by the links between the parameter field and the known geology, then I cannot reject the hypothesis that this bad thing will happen. And there's no Gaussian assumption involved in here. And if PEST needs to connect permeability, my God, it will. If it needs to connect impermeability, it will. Because we're working in a highly parameterized world, PEST has the freedom to do whatever we ask. Then we decide whether the fit with the past is good enough, or whether the parameter field which emerges from this process violates common sense. We decide whether we reject the hypothesis. So this is a model from many years ago, but this model taught me an awful lot about modelling. So this is an area about 1,000 kilometres north of where I live. It's a farming area, and a lot of water is extracted here for irrigation. As you can see, it's a very volcanic area, and the government said it made a rule, no more water to be extracted from this basalt aquifer because it's impinging on flow of water in the streams. Now, and that stream is the habitat for some species that their neighbours are allowed to pump plenty of water out of the ground. Why can't they? And this is the same story all over the world. Sooner or later, the line in the sand has to be drawn. We can't extract all the water we want and protect our ecosystems at the same time. And the first people to find themselves on the other side of that line are going to be pretty annoyed. And these farmers were pretty annoyed. So they contracted a friend of mine, a geologist, to help them build a case to take the court. The geologist asked me to build a model. And I wasn't particularly sure why I had to build a model, but he said we need to build a model because if we're going to go to court, then it looks better if we have a model. And that's often the reason that we build models. That's when it comes to think of it. So I built a model. Here's as you can see, the topography. It's recent volcanism. And so I built a single layer model. The geology, basalt is green, Precambrian schists and gneisses are blue, alluvials in the valleys and granite on the hill. There was measurements of varying quality in a number of wells. Recharge was estimated using salt mass balance, chloride mass balance. Measurements of inflow to these two streams were available between these gauging stations. So I calibrated the model. I was able to replicate heads pretty well, replicate inflows to the stream segments. There was inflow just in one of those three segments in each one of these streams. No problem replicating that. Came up with a pretty heterogeneous transmissivity distribution, but every time I work with basalt, the story's the same. Basalt can be extremely extremely transmissive in some places and extremely resistive in others. The calibrated parameters were transmissivity and drain conductance, water is allowed to find its own point of escape from that basalt aquifer, which is sometimes confined to the surface. So now we come to the prediction. This farmer who has this well wants to pump water. Yes, he's beside the stream, but there's 2 metres of impermeable clay between the well where he's pumping and the stream. He says when he pumps, he won't deplete the stream. He's pump tested. One geologist interpreted and said there's no link with the stream. Another geologist interpreted it and said there is a link with the stream. So that hasn't told us too much. What can the model tell us? So I ran my calibrated model with him pumping from his well, and the prediction was that when he pumps, he'll deplete the stream. I did uncertainty analysis and showed quite conclusively that when he pumps, he'll deplete the stream. The only thing I hadn't done was ask PEST, the only question that really mattered. Is there any way that when he pumps, he doesn't deplete the stream? So I now recalibrated my model. And I recalibrated the model, which is now run under historical conditions and under future conditions. And I observed that he doesn't deplete the stream. I said to PEST, PEST, I don't care how you do it. Come up with a parameter set that makes him not deplete the stream, but also fit the past and come up with reasonable parameters. Now, what I expected to happen, I put more and more weight on the observation that he didn't deplete the stream, and I expected to come up with this thing called a Pareto front, which measures what I've got here is the weight that I place on that hypothesis versus what I expected to see of the objective function, which measures model to measurement misfit under historical conditions. Basically, I expected to demonstrate incompatibility of that prediction with the historical behaviour of the system because I'd uncalibrate the model. I was sure this is what I would see. Instead, the objective function rose for a little while and then it fell again. It looked like PEST was finding a way. I got just as good a fit that I got with the historical data set as I did without that prediction as a member of the calibration data set. The calibrated transmissivity field was no worse. The conductance field was actually a little bit better aligned with the geology. I was able to fit inflow to those stream segments, probably in a little better place, a little bit aligned with some structure that you can see with the eye of faith running through here. And when he pumps, he depletes the river, not the stream. And there's a lot more water flows down that river than what flows down the stream. So what's the answer at the back of the book? What's going to happen if he's allowed to pump? The official answer is, I don't know. And I've processed all the data that I had available, and I was able to demonstrate that that data does not allow us to distinguish between two possibilities. Now, decisions still have to be made. It's not my job to make decisions. It's my job to tell people, in this case, that you're going to have to make this decision, not on the basis that you know what's going to happen, but on the basis that you don't know what's going to happen. And it all depends on whom is the onus of proof, the farmer or the government. But meanwhile, I've given the decision-making process all the information that can be given. I've not given them an illusion that the model says this will happen or that will happen. Modelling has said we don't know. The decision still has to be made, but I've done all I can. So in conclusion, I hope I've said something that'll change your mind a little bit about how we should approach decision support modelling. It's not about building a giant, great, big, ugly numerical model and then history matching as an afterthought. It's all about building a model from the ground up to implement Bayes' equation, using as our tools the partial differential equations of groundwater and contaminant flow, but using them to serve Bayes' equation and using Bayes' equation to assimilate whatever information is at hand to quantify and reduce the uncertainties of decision-critical predictions, and to tailor that modelling process from the ground up to be something that can give numerical voice to Bayes' equation. And in my experience, that will not mean necessarily a structurally complicated model. It will normally mean a model that has a lot of parameters, but possibly housed in a structure that's comparatively simple, but that allows that model to run fast, gives it numerical stability, and show us through the parameter fields that emerge through the history matching process, not a picture-perfect representation of what's under the subsurface, but a lot of information that's about what is under the subsurface that'll allow us to see what we can know and what we cannot know and what implications we are able or not to draw about what will happen to a system once we start managing it in a certain way. And with that, I finish the talk.
Thank you, John. Let me take 3 seconds of silence just to breathe in the content of your talk, which seriously, I really loved it. You know, that uncertainty analysis, uncertainty quantification, and sensitivity analysis and stochastic inverse modeling has been at the heart of my research since all my life, so I loved it. So I really appreciated your talk, so really very much.
Thank you, Alberto.
You gave me a hard time, now it's my turn to give you a hard time. So if you don't mind, if nobody else minds, I will take the privilege as chairing the session to ask you the first question. Okay. And then if Sheen is okay, I will ask Sheen to ask you a question, and then we open the general discussion. Okay. Amongst the several questions or topics that I had in mind, I wanted to ask you some comments about the concept of uncertainty, because you showed interesting results and provocative results about contributions of parameters to uncertainty and worth of having future data, let's put it like this, of collecting future data in space and or time, by ranking this worth in terms of contribution to reduction of uncertainty. Maybe I got a wrong impression. I thought for some reason that throughout the talk, the concept of uncertainty was limited to the, let me call it in a simple way, the variance of the distribution of the model output. Don't you think it is a little bit too limiting as a concept? Because, for example, parameters can contribute to the mean of the population of the output, can contribute to the extreme values, so to several moments of the output. What is your view on this?
Oh, well, you're right, of course, Alberto. And is it a simplification? Absolutely. It's simplified because, yes, well, there's a lot of simplifications. Firstly, the definition of contribution to uncertainty. The definition, I mean, that's short for what would be the uncertainty if I had perfect knowledge of those parameters. And I just loosely call that contribution to uncertainty. And it's a contribution to the variance of the prediction. So yes, it's a few words for an easy concept, which is really a much more complicated concept. Nevertheless, I would argue that given that we don't think about this enough, a simple statement that can help people think about this is a good stepping stone to help people. Is it the full story? Absolutely not. But it's a better story than most people are aware of at the moment. And if they want to know more, I'll tell them to see you.
I knew I should have shut up when asking this question. Well,
don't ask me, ask Alberto.
No, I totally agree. And the key point was to raise awareness of the concept of uncertainty. Then there are several ways of quantifying it, and we all agree on that. And I truly appreciated the way you brought it in. Shin, would you like to ask a question?
Yeah. So hello, the audience. My name is Xin He. I'm a senior research engineer from the China Institute of Hydropower and Water Resources and Hydropower Research, IWHR. So first, I'd like to thank my employer, IWHR, for sponsoring this web event. And second of all, I'd like to remind you that what we are seeing today, the video, the PowerPoint slides will be uploaded to our website, maybe tomorrow or the day after tomorrow. So if you missed anything and you want to rewatch the videos, please come back and check on the same website. And for you audience, viewers sitting in front of your computers or smartphones, you are more than welcome to raise your questions. Just write your questions in the comment section on our website, and we will, Alberto and I, we will select questions and pass them to John. So for myself, my first question to John is, I'm a sort of a long-time PEST user, but my knowledge about PEST is sort of the old-fashioned gradient-based Levenberg-Marquardt search algorithm. So to me, PEST is used to sort of do the last mile of your long journey. You already have a pretty good idea of your parameter values, and you use PEST to fine-tune your selected parameters to make your model approaching to perfect, or the not perfect, but the ideal model you are pursuing. But after hearing your talk today, I feel like there is much more to it. So you can probably use PEST or PEST ++ to assist your modeling practice all the way from the start. Is that right? I mean, if so do you have any advice what we should do?
Well, I'm normally, when I build the model, I'm pretty lazy. So I built the model, and then I just basically do what I showed in those examples. I normally then give, so the parameters that I give to the model initially, I'd like to think of are in the center of the prior probability distribution. So that is, they're the best parameters from an expert knowledge point of view, knowing that the uncertainties are mile wide, but still, they're the best parameters, lots of them. And then I just hit the button and let PEST do the rest. Now having said that, I don't accept everything just because PEST told me. Like, if parameters are really stupid, and if that's what it takes to get a good fit, then PEST is still telling me something. It might not be telling me what I want to hear. It might be telling me that these parameters are taking on roles which are compensating for model defects. And in fact, most times that I build a model, any of us build a model, we learn a lot through history matching. And there's always surprises. Some of those surprises are that the geology isn't what we thought it was. And some of those surprises are that our model isn't what we thought it was, and that if parameters have to adopt stupid values to get a fit, it's telling us we need to revise the conceptual basis of the model. Now, sometimes for certain types of predictions, stupid values are okay. It gets a bit subtle. Other times, they're definitely not. But in either case, PEST is telling me something that I wouldn't find out if I wasn't using PEST, because by getting the best fit that I can straight away, without holding back, making sure I don't vary the parameters to their stupid values, if the PEST is determined to make parameter values stupid, I need to know. And I need to know why, maybe adjust the model, maybe decide not to care, but it's my decision. So for me, I build a model, try to make it sleek, try to make it fast, put all the parameters like you saw that it needs, and run PEST, and then go from there. And that could be the start of a lengthy model revision process, or very, very rarely, the model's calibrated, I get beautiful fits, and I can solve the inverse problem, I can solve the invoice problem, get the model out the door and get on to the next model. But that doesn't happen very often. Mostly you've got to make substantial changes to the model, which PEST has told me what I need to make.
All right. We have a question from one of our viewers. I don't know who that person is. I mean, if you are writing your questions, maybe you could identify who you are and where you're from. But if you want to stay anonymous, that's okay too. This person wants to ask you, what do you think are the main limitations of PEST?
Well, nothing's perfect. Well, and there's a broader, like there are a lot of methods that we can use. Now in the beginning, and I have to say, in the beginning, PEST just used the Gauss-Marquardt method. In the beginning, it couldn't accommodate non-uniqueness. And then I incorporated things like singular value decomposition or equivalent methods that would allow it to. Now, if I had my time again, PEST is doing things now that it was never intended to do in the beginning. Internally, parts of the PEST code are a nightmare. It needs to be rewritten, but it's time for the next generation to rewrite it. So we turn to PEST++. It's more modular, written in C++, as the name suggests. So one of the things about PEST is that it's a little bit difficult to use by virtue of some of the concepts have been modified from the original concepts. In terms of the methodology itself, the biggest problem, now the setup for parameterization of a model, that is not easy. And one of the problems I think we have in our industry is that the graphical user interfaces that we have are beautiful at giving us models, but not good at the data assimilation thing. That parameterization, how we formulate objective functions, how we history match are more of an afterthought. So we don't get much help as we would from the beautiful software that's available, for example, in the petroleum industry. So a lot of people are saying, I'll do this myself, and they're using Python scripts to do the setup. And that's a totally valid thing to do, and maybe the answer, particularly in our industry, where we don't spend a lot of money on software. The other thing about PEST itself is that it does use that gradient method, so we have to calculate a Jacobian matrix. If you've got thousands of parameters, that can take thousands of model runs. Ensemble methods, you don't need that many model runs, but you don't get your minimum error variance solution. So there's positives and negatives. Nothing's perfect. I hope I've outlined a few negatives in using PEST. Some of it is because of PEST itself. Some of it is because of the methodologies that it uses, and some is because setting up this whole parameterization and objective function definition thing is always going to be one of the hardest parts of decision support modeling, and it's the part that we get very little help from in current commercial or non-commercial software.
Okay, thank you. The next question is probably coming from a Chinese viewer because I have that question too. I mean, you mentioned that it's better that we use a lightweight model that can serve one purpose at a time, work, right? But when we at work, when we have to do consulting projects, we don't get used to choose. We don't get to choose which model we use, and that model can be a very heavy one. It can be huge and serving multi-purpose at the same time. So if you're using that kind of model, what suggestion do you have if you want to use, PEST for your model calibration?
Well, that question isn't just faced in China, it's faced all over the world. And I think there's an expectation everywhere that a model isn't any good unless it's big and complex. So it's not just China. Okay, so what are your options here? Now, I have to say I'm giving a webinar in a few weeks on the subject of model complexity. And this is one of my pet themes. So there's two answers to your question. What can you do if your model takes a long time to run and is numerically unstable? Well, the first option is to give up. The second option is to continue the charade, come to some, calibrate it somehow and then deliver it and pray that people don't actually use it to make a decision. The third option is you can try to use PEST. You can parallelize model runs. But, there's a paradox here. If you've got that much structural complexity and you complement that with parameterization simplicity, what have you got? You've got a simple model in disguise, which you've paid a heck of a lot for and which pretends to be something it isn't. The process isn't working. So I'd say your only option in a case where the model is big and heavy is to use ensemble methods. Try to use lots of parameters and then go straight to ensemble methods, because even if you have a lot of parameters, those methods will get you, hopefully, history matched with the smallest number of model runs. But if the model is numerically unstable, ensemble methods will become unstuck, because if there's anything that an unstable model hates, it's a random parameter field. It'll fail more often than not. So the other thing too is, I think, and this is verging into my pet interest, I think we have to ask people who are telling us to build these models, who should be designing the modeling process? Modelers or other people who think they know something about modeling? And one thing that I've found after all my experience is the less you know about modeling, the more faith you have in models, particularly in complex models. And that once we modelers get to do this decision support modeling thing as it should be done, we should perhaps be a little bit more vocal in telling people who ask for models that these great big complex things are not doing the job because they're not fulfilling the fundamental imperatives of quantifying and reducing uncertainty. Alberto, do you have a comment on that? Like, you would have thought about this issue a lot yourself.
I'm not sure. I'm really not sure at this point. So, because I really don't understand your bottom line. I mean, at the very end. So,
well, we have many questions coming in. Should I go to the next one? So this person asks, he or she is probably working with pilot points. So the question is, besides kriging, are there any other interpolation methods available in pilot points in PEST?
Yeah, now the answer is yes. So it's not actually PEST. Like PEST doesn't know anything about parameters. It is model independent. It's the software that comes with PEST that looks after the parameterization. And the package that handles pilot points is called PLProc. It's downloadable for free from the PEST website. Now, it provides 3 methods of interpolation: kriging and a few variants thereof, simple kriging, ordinary kriging, radial basis functions, and inverse power of distance. Most times, the function that I use is it's a kind of an adaptive kriging. It's a kriging that allows me to have different densities of pilot points in different places, and it automatically adjusts the variogram that it uses to do the kriging to accommodate the different densities of pilot points. Now, that I prefer best of all. For a while there, I was wedded to radial basis functions. Then I changed my mind. They're a little bit too oscillatory. So I think, but the trouble with kriging is that if you got very different densities of pilot points, using the same variogram doesn't work very well. So using this adaptive function in PLProc that can adjust its variogram to pilot point density does the job most times.
Okay. And John, there's an interesting question from Richard Serda from TU Darmstadt. And the question is whether you would recommend PEST, the way it is right now, to deal with extremely nonlinear problems, for example, unsaturated zone flows.
Now, yes and no, but see, the problem is if I say no, what is plan B? Because extremely nonlinear problems challenge everything. So if you only have a few parameters, just a drink of water here. If you only have a few parameters, then and especially if a problem is so non-linear as to create profound local optima, then it's possible you need to use a global method. Now, there are a couple of global methods supplied with PEST. There's particularly the CMAES, that's Covariance Matrix Adaptive Scheme, which uses an algorithm that from the literature from a German colleague whose name I forget. But there are other global optimizers around too. That's the sort of method of last resort. To do uncertainty analysis, you could use something like Markov chain Monte Carlo, of which Dream, written by Jasper Vrucht, would be very good. But the trouble with those methods is that they're sort of limited in how many parameters that you can use. But if it's just a one-dimensional Richards equation model, and that's not going to have a lot of parameters, so something like Dream could work fine. But if you've got a 2- or 3-dimensional model with saturated, unsaturated flows with hundreds, thousands of parameters, then really the only thing, PEST may work. Ensembles often work a little better in that case because you're using ensembles, they tend to be able to reach further into parameter space and jump over local optima. But highly nonlinear models also tend to be delicate models, and they may not work well with ensembles. So that's the long answer to your question. PEST from different starting positions may work just fine, but try ensembles as well. I can't guarantee anything will work. I can't guarantee that that one particular one will work better than the other.
Well, following along these lines and considering the non-linearity, let me talk about non-linear models. Critical, let me call it parameter for a very specific reason. In this case, is the grid size. Okay. Would you consider the grid size also as a parameter to be estimated in these cases on the basis of data? I know that we are going into a delicate field talking about numerical accuracy. Okay, I fully understand that. That's why I just wanted it to be very provocative, this part here.
If it works, it works. Like as I intimated during the talk, models are abstract things, and if if the grid size for a particular purpose needs to be tuned to the problem at hand, and if we know what the repercussions of it are, and if a particular grid size or modelling approach allows us to assimilate data that we otherwise couldn't, as long as you satisfy yourself that you're not biasing some prediction, or that any bias that you induce is included in the uncertainty, do whatever it takes.
That would have been one possible conclusion. So you can, maybe yes, maybe not, quantify some sort of numerical error or truncation, and then you should reflect this into the uncertainty associated with your prediction. This is what you're saying, right?
Yes.
Yeah, okay. Got it. There are then two questions, one from Pierre Serafin from France, and the second one from Srikant from CSIRO, okay, who says hi to you also, by the way.
Hi, Srikant.
To me, they're very similar, and the point is related to parameter uncertainty, highly parameterized models, and the structural uncertainty of a given model. I'm assuming that both questions are not related to the mathematical structure of the model, but otherwise to the geological structure of the system. And so the key point was that whether first, if high parameterization means also coming up with reducing structural uncertainty of the geological model, okay? I'm paraphrasing because the question is about structural uncertainty of the model. I added the word geology, and the second one was related to use different models, and I'm assuming hydrogeological, so geological settings. And then use each of them separately and address somehow the concept of equifinality. Okay, what are your thoughts about that? I tried to summarize as best as I could the two questions into one. Okay.
Firstly, there's no one answer here. So I think the thing about modelling, it's always going to be individual. And I have no problem with that. There is no one way to do it as long as you can justify what you're doing. Okay, now, there are many facets to those little diamonds of questions. The first, is so can perhaps you use different models to embody different geological concepts? Absolutely, if you're not sure of the concept, of course. Having said that, if by virtue of a little abstraction, you can let parameters do the work of different concepts, if you can create a continuous parameter field that can mimic the different concepts, you'd be better off. Just the numerical work that has to be done, and just your ability to allow those parameters to explore even more possibilities than two categorical concepts. Having said that, that won't always be possible. You've just got to do what's possible. So for me, I always try to do things with continuous parameters, and if the price of being able to cross categorical thresholds is a little bit more abstraction, I'll try to do it, but I acknowledge that will not always be appropriate. Secondly, in terms then of unrealistic parameter values, this starts to get complicated. This depends on the prediction. So, you can show that if your prediction is what I call entirely solution space dependent, if the past is entirely informative of the future, then goodness, machine learning will do the job for us. and a model that history matches well, even if parameters have to adopt surrogate roles, bias in parameters does not translate into bias in certain types of predictions. So you can get away with murder. But for other predictions made by the same model, you've just done a dastardly thing. So then that whole thing does become prediction specific, and a strategy that could work for one prediction that would allow parameters to take on outrageous values would not be allowed for another prediction where taking on reasonable values and a more complex structure that doesn't require such abstract parameters would be the better path to take. So again, different models perhaps optimized for making different predictions. But in the end, it'll be a personal choice. The only thing I ask of people is that they familiarize themselves with the concepts and be aware of the fact that it is your choice and someone else shouldn't tell you to build a great big model if you don't have to. Know enough to tell them, go and build a model yourself. I'm doing it my way.
Okay.
Thank you. I think you introduced an important concept, which is related to the possibility of constructing a surrogate of a given model, which is also related to one of the other questions and also to one of my questions. So I will try to summarize this part into a comment and a question. So starting from experience, for example, I was involved in a project which was related to ground risk assessment related to possible contaminations, for example, of groundwater associated with shale gas operations. Okay. Now, of course, when you talk about multi-phase flow models, and then you have to consider migration of different phases up to the shallow aquifer systems, then of course it can take a lot of computational power. Okay. And yeah, I can agree that computational power is not an issue, but it is an issue, depending also, and it is an issue also depending on time constraints that you have to take a decision. Then we can argue about whether or not, if you do not have the time to take a decision, just postpone it. I don't want to go into that. That's not the point. So in some cases, you need to go, or you are required to construct some surrogate models. The weight, the burden to construct these surrogate models depends also on the, by models I mean mathematical models, not geological models, okay? The burden to construct them, well, it depends on how many parameters you want to include into those surrogate models. Therefore, you try to assess which parameters are more important than others. Of course, you need to define the concept of importance of a parameter. Let me use it loosely, okay? Which somehow goes a little bit against what you were suggesting by saying, you know, I actually would like to use all parameters which are associated with a mathematical model. And but then sometimes you don't do it, you cannot do it. So how do you deal with that? And what are your thoughts about that?
Well, exactly as you say, but I am happy to make all embracing statements for the sake of entertaining people. But and I think that a lot of us coming off a lot in groundwater modelling don't realise the possibilities that are open to them. Having said that, you know, I think we need to know about the benefits of highly parameterized inversion. But as you point out, if you can't reap those benefits because you have to build a surrogate with only the most important parameters, then there's no choice. So there's no one rule for everything. I'm not going to suggest that for one moment. Just know the only rule is know what you're doing and make the best choice for the occasion. And it's always going to be a compromise.
Yeah, because also in these cases, what I found interesting was that, at least in our experience, you can always work, if you feel like, with local, global, whatever sensitivity analysis you would like. And then you can either work on your mathematical model or on the objective function. Working on the objective function, it is related to your capability then of calibrating a model. Working on the model itself increases your knowledge about the behavior of the model. Doing both is of course recommended, but sometimes it's just not doable. Okay. So if you had to choose, would you like to work with a model that you actually do not know? I'm doing it on purpose, asking this question, okay, just to provoke some discussion, okay? Or would you start with the objective function? Whatever objective function is. Okay? I told you, you gave me a hard time during the presentation, now it's my turn.
I'm going to say, I'm going to probably give you the answer you don't want to hear. I'm going to say I don't think, I think I could only answer that question when I am totally familiar with the decision that has to be made and the prediction that has to be made. And I'm sort of hope that after all this experience that I'd never, I would hope I would never lose sight of the prize. And the prize is someone, there's a bad thing. Like I said, there's a bad thing, and I have to illuminate the possibility of that bad thing happening. Now, if I cannot extract information from history matching because the model's not up to the task, and I have to put limits on what I extract on account of not going to the place where I'm actually biasing parameters and getting disinformation, I would hope that I would recognize that point of no return, live with the fact that a mediocre fit is all I'm going to get, and then say this is the best that can be done with the technology we've got. And it will be a context-dependent decision, and no two contexts will be the same.
You know, I tend to agree with it, and it's some sort of goal-oriented model optimization. So first you start from the question, and of course you come up with a probability distribution of model parameters which help you address that question, and not necessarily other questions, maybe in the same area, maybe. Exactly. This is what you wanted to say, right? I agree with that.
Exactly.
I agree.
Yeah. Okay, let me take some questions from the viewers. There are people asking about if PEST can be used in seawater intrusion modeling or groundwater and erosion modeling. I guess the answer is yes, but do you have any recommendations? What should they pay attention to?
Now, seawater intrusion modeling is something I've done little of, and I'd like to learn a lot more. Now, I am not an expert on seawater intrusion modeling. However, the difficulties, the nonlinearities, and if one is going to attempt to simulate full density dependent flow, there's a major problem here with the type we've just been talking about. Long run times, delicate numerically, highly nonlinear. Now, firstly, I'd say, are there any alternatives? I think that there's so much uncertainty here that we are justified in looking for a simpler approach. And some of the methods pioneered by people like Otto Strack, you know, the potential that the methods that he uses based on a saltwater potential embodied in code such as ModFlow SWI may have potential here. I wish that code was a little bit more stable than it was. But firstly, I would suggest there'd be a lot of situations where you don't necessarily have to do full saltwater intrusion modeling to solve a coastal problem. Secondly, if you do, is there an alternative to full density dependent modeling? Thirdly, if there's no alternative, then you got a hell of a problem. Probably ensembles are going to be a lifeline there.
Right. And what about erosion, groundwater and erosion?
Yeah, now now I don't know much about that either, but that's pretty non-linear. Like it's worth a try. Like there's still got to, whatever modeling you're doing, if there's data and you can't assimilate it, what's the point of gathering that data? Now, if the model is unstable and unhealthy, then as Alberto says, you may have to build a surrogate. You may have to put up with a less than perfect fit. You just may have to get the best fit that you can. And there's a growing amount of literature emerging at the moment about so-called structural noise and how you can actually take into account your lack of ability to get a perfect fit in the uncertainty that you quantify with a less than perfect fit. And there will be times, many times, as Alberto says, with highly nonlinear processes, that's what you got to do. So I would always look for the simplest way out, but if simplicity compromises what you're trying to do, then it's not a way out at all. Mm-hmm. In that case, you live with the complex model, you live with a less than perfect fit, and you do your best to incorporate the less than perfect fit into the uncertainties that you quantify.
Okay, thank you. The next question is actually from myself. I always wanted to ask you this, John, a long time ago. I used to work in Europe, now I'm in China. So I have like a problem when I talk to the local or national water managers or the decision makers, because in their mind, the world is sometimes black and white. So there is a good model and there is a bad model. And as modelers or as scientists, we know it's not that simple, and we have to sort of somehow communicate the concept of uncertainty with them. So how do you, what do you suggest, what we can do to communicate with the water managers in terms of the uncertainty issue about our models?
Well, that's a common question, but can I say that the things that, firstly, things are changing. I think that people are becoming more and more aware that you can't ignore uncertainty. Now when it comes to to managers, managers tend to be, why are they managers? Because they're not as smart as us modelers, for a start. So you have to be kind to them and pat them on the head and sympathize with them. Don't offend them. But then managers are also scared. They're scared of their political masters. So the argument is, well, this is what the model says. You can just say, well, that's very courageous of you, manager, through doing exactly what the model says without taking into account that models can be very wrong, and the penalties for being very wrong could be very considerable. But you go right ahead and do what the model says. Very courageous. So if you talk to them like that, they might soon realize that treating the model as a crystal ball, they're the ones that could get into trouble, especially when there's growing realization around the world that that's yesterday's way of thinking. Oh, that's another good line. Tell them that's very courageous of them sticking with yesterday's ideas when the rest of the world is moving forward. That might work as well. And if that doesn't work, tell them to call me and I'll talk to them.
John, as we are approaching the end, I'm going to ask you one last question, if you don't mind. And it is related to a key aspect of the presentation, which was the evaluation of what you called of the posterior probability distribution, let me call it, of parameters. I just want to make sure that I understand completely, because the way I understood from what you said was that you have different realizations of your model, and then for each one of them, you come up with an estimated set of parameters. Then you take all the estimated sets or the estimated values of a given parameters and you construct the marginal. What I'm wondering is, by definition, what you get from each of these model realization, and by model realization, let me say, for example, geological realization, geological settings, okay? From each one of them, and each one of them can be considered as a different model, okay? From each one of them, you come up with an estimate of parameters, and of course, its own uncertainty, and which is associated with the covariance matrix. So I'm not sure that properly you are coming up with what you call a posterior distribution of parameters. What you come up with is a frequency distributions of best estimates of parameters. Why, for example, to come up with a posterior, you should somehow resort to a different strategy, which is, for example, acceptance rejection, which is, of course, can I say suicidal? Because it employs, it depends on the acceptance ratio, okay, on that. Am I right in understanding, interpreting what you said? Or did I understand?
I hope I understood your question correctly, but
the point is that,
yeah, go on.
The point is that what you get are, for each model, you come up with an estimated value of a given parameter. And of course, if you have more than one parameter, then you have the associated covariance matrix, of course, okay. Then you go to model number 2, you have an estimated value of the same parameter, which is different, of course, from the previous one. And then you come up with a frequency distribution of the estimated parameters, which is not necessarily equal to the posterior of the parameters, because you're not sampling directly from the posterior of the parameters. Am I right?
Yeah, so just to get, so we're not at cross purposes with the terminology, so I'm assuming the model structure is correct.
Sure. Okay.
Now, there's theory which says that if the model structure is correct, if the world is multi-Gaussian, then the samples which you get from using the ensemble methods are actually samples of the posterior. Now, do you have enough to fully define that posterior? No. Is the world multi-Gaussian? No. But the theory, and I'm not an expert on this theory, but the theory is there that what ensemble methods give you under a fairly restricted set of circumstances is completely in accordance with Bayes' equation, of which rejection sampling is also in accordance, but infinitely harder work.
Okay, got it. Thank you.
Of course, none of those assumptions are met in practice. So there's uncertainty in the uncertainty. But the beautiful thing about uncertainty is if you say something's got a 95% probability, reality is only going to happen once. No one will ever prove you wrong. So uncertainty is a good business to be in.
And just really before we wrap up, I think that's a very important question from Alexander in Canada. And what is the best way to get trained on how to use PEST? I think this is of interest to all the audience.
Well, not just PEST, but PEST++. If you go to the GMDSI website, there'll be links. So there's training material there. I've done quite a few videos on PEST. You'll also have links to the PEST++ site, where a colleague of mine, Rui Hugman, is doing tutorials on setting up for PEST and PEST++. And then there's PEST++ has its own set of tutorials, mainly using Python scripts to do the setup. So I'm not going to say it's all easy, but there are resources. And so let me direct you to there. There's also, I mentioned before, HydroSimple, which is starting off courses now with modeling, including PEST. So there are places that you can go. I wish I could say there was one beautifully bottled course and you'd come out an expert, but, well, there isn't, but there are resources and plenty of them.
Lovely. I think it's time to wrap up now. And I would like to thank John for the wonderful speech. And John, your availability also to cope up with all my nasty questions. Okay,
They weren't nasty.
They were not meant to. Okay.
Oh, fine. I mean, you brought up points that I didn't, Alberto. That's fine. That's good.
Thank you. Then Xin and all the IAHR office in Beijing and all the IAHR organization and the groundwater management committee and would like to ask all of the audience for being here and coping with us in our discussions. And I think you really brought up an important point and did it very nicely, John. I really appreciated it. The concept of uncertainty and how complex is the very definition of uncertainty and a way to properly deal with it, whatever properly means, because you never know. You need also the definition of properly coping with uncertainty.
I don't think properly has a definition.
I agree with that. And I couldn't agree more. Also the concept of uncertainty quantification targeted to a given objective, which can change depending on the objective and on the scope of the practical engineering and environmental application. So all in all, from a personal standpoint, I consider this webinar as a huge success, and thank you, John, for being here.
Thank you.
And thanks to all the audience. It was a pleasure for me for being here. Xin, any last words that you would like to add?
No, actually, but thank you all for being here. And if you want to rewatch the video, please come back to our website. Probably tomorrow.
And Xin, thank you for organizing this too. You're the force behind this. Thank you.
Yes.
Yeah. Okay.
Wonderful. Thanks to everybody. Have a great rest of the day or evening or morning. Bye.
Bye. Thank you.
Bye-bye.
Bye.